Hi, my name is Gwen VanLeeuwen, and I am a senior in mechanical engineering at Kansas State University. I'm working with Dr. Scott Fan in the Department of Mechanical and Nuclear Engineering. Today, I will be presenting my research on developing an on-site microplastic testing device for Kansas water. Micro and nanoplastics are a significant environmental issue where they are increasingly contaminating various water sources, which include tap water, bottled water, ponds, and lakes. These plastic particles impact water resources in multiple ways, including food production, water treatment, and ecosystem sustainability. There are current technologies for analyzing microplastics. However, they are complex, costly, inefficient at concentration, and not readily accessible. This makes widespread and on-site analysis very challenging. This research aims to develop a more efficient solution by integrating a microfluidic chip with dielectrophoresis, or also known as DEP, to quantify, collect, and detect microplastics in Kansas water. Microplastics from a water sample will be concentrated using DEP on a microfluidic chip, which will then be detected by an electrical sensor to provide an on-site testing device. The design of the microfluidic chip will involve testing different patterns, voltages, and frequencies to generate movement and manipulate the plastic particles within the water droplet. This is done through DEP. DEP is when a particle exerts a force, called a DEP force, when present in a non-uniform electric field. This causes the particles to move within the water droplet. As shown in the equations, DEP depends on voltage and frequency, which are the variables that will be tested in this research. By applying DEP, the plastic particles can be directed to concentrate on pattern electrodes embedded in the microfluidic chip. Initial experiments were tested from voltages ranging from 40 to 72 volts and frequencies from 1 to 9 kilohertz. A constant finding showed that as the voltage increased, the speed and efficiency of the plastic particles increased as well. In figures 3 through 6, this test consisted of polystyrene particles of 3 microns in diameter. This was a 2.5 microliter droplet at a very large original concentration. Through the photos, it is clear to see that as the voltage increased, the concentration becomes more defined. The particles are more concentrated at 64 volts than at 40 volts. Although more voltage was applied on a separate test, which is seen in figure 8, the high voltage caused damage to the chip that made it unusable. This confirms that figure 6 shows the final optimal result at 64 volts and 1 kilohertz. Building on these results, future research will focus on experimenting with different frequencies and flow rates to be able to sort by size and various types of plastic particles. Pre-processing methods for large water samples will also be explored, along with the design of a new chip pattern to improve concentration efficiency. Lastly, an electrical sensor will be applied to detect electrical signals from the plastic particles. Based on the current results and future direction, this research continues to develop an on-site, user-friendly testing device that can advance field-based analysis of microplastics. Thank you for listening.